Hello everyone. Today we're going to go through a few more related rate problems. We're going to cover questions 8 through 11 in your notes. So let's get started. A 2-meter tall statue is being moved at a rate of 0.4 meter per second away from a lamppost with a light that's 5 meters above the ground. We need to answer two questions with this problem. First off, at what rate is the tip of the shadow of the statue moving away from the base of the light post? Second question, at what rate is the length of the shadow of the statue changing? So it would be a good idea to start by identifying what we know and identify what we don't know. We know this lamppost is 5 meters tall. We know the statue is 2 meters tall. I'm going to go ahead and call the distance of the statue from the lamppost x, and I'm going to call the distance of the shadow from the lamppost y. So light from the lamppost will form a shadow when it interacts with the statue like that. And this distance we'll call y. This is a really great problem. When you read it at first, it might seem nearly impossible to answer. And it's ultimately not the most practical problem, because when would you ever care to know this? But we can do it. Before we go any further with this problem, we can actually play around with this on Desmos. I've provided you a link in the description, and here's what it looks like. So we have a slider here that can manipulate the distance of the statue. This red circle is meant to represent the lamppost. This purple line is meant to represent the height of the statue, and this is where the end of the shadow is. So you can play around with that a little bit and see how the problem works. So at this point, I'd recommend you pause the video and, using Desmos, fill out this table with statue versus shadow distance from the lamppost. And as you go further along, see if you can predict what the shadow distance will be. At a distance of 0 from the lamppost, the statue is 0, the shadow is also 0. At a distance of 1, the shadow is 5/3 from the lamppost, or 1.6 repeating. At a distance of 2 from the lamppost, the shadow is 10/3, or 3.3 repeating. At a distance of 3 meters, it's 5. At a distance of 4 meters, it's 20/3, or 6.6 repeating. And at a distance of 5 meters, it's 25/3, or 8.3 repeating. So once you've filled out the table, that's what you should have. And you can try graphing that. And here's what it looks like. The graph is described by this equation. So something you should notice at this point is it's a linear relation, but question is why the 5/3? So in order to answer that, we're going to have to look at the geometry of this problem. If we go over to our diagram and draw a horizontal line from the statue to the lamppost, notice that this line is parallel to this one. This is also a right angle, and this is a right angle. That if the height of the statue is 2, that means this height here is going to be 3. And if you look at this red line as a transversal hitting two parallel lines, you'll notice that this angle corresponds to this one. So I can recognize two triangles here. This one up here, with this length being 3, and this one being x, and this angle being theta. And then this larger triangle, with that length being 5, this length being y, and then there we have it. So this is also theta. So one thing we can do is write a relation between this side and this side, including this. So notice we have the opposite and adjacent side. So we can use tangent, which is 3/x. As x increases, this theta also increases. So this is not a static quantity, nor is this, but this equation will hold true because this height will never change, that's constant. So theta is related to x with this equation. And we can do something similar with this larger triangle. This side length is 5, that would be the opposite. This side length is y, that would be adjacent, and that's theta still. So tan theta equals 5 over y. So what we can do next is actually merge these equations. They both equal tan theta, so by the transitive property 3 over x equals 5 over y. And now we have a relation between x and y. We can write y equals 5/3 x. And that's the key to solving this problem. So first off, we can answer the first question. At what rate is the tip of the shadow of the statue moving away from the base of the light post? So what we really need here is dy dt. Now we can use chain rule and write dy dt. So if we find dy dx and sort of multiply it by dx dt, these two will sort of cancel, for lack of a better word, and then we end up with dy dt. So once we find dy dx, which we can find from this equation, and dx dt, which is given in the question, we can figure out what dy dt is. So let's start by finding out what dy dx is. We can use this equation. Dy dx is simply 5/3, and then dx dx is just 1. So dy dx is 5/3, and we know dx dt, which is given in the question, is 0.4. So all we need to do to figure out what dy dt is just multiply 5/3 by 0.4. And when you multiply 5/3 by 0.4, you get 2/3, or 0.6 repeating meters per second. And that gives you the answer to part A. So that is the speed at which the shadow is receding from the lamppost. So part B is asking us to find the rate that the length of the shadow is changing. The shadow is given here. So we can figure out the length of the shadow by subtracting x from y. That will give us that. So the length of the shadow is y minus x. We know from earlier that y is 5/3 x, so I can sub that in for y, and I can simplify this. So 5/3 x subtract 1x will give me 2/3 x. So the length of the shadow is given by that. If we need to find dl dt, we just need to take the derivative of this with respect to time. So that will be 2/3 dx dt. And we know dx dt from earlier is 0.4. So multiply 0.4 by 2/3, we get 4 over 15, or about 0.26 meter per second. Next question. A hot air balloon is 60 meters directly above SAM and maintains its altitude even when wind is blowing it horizontally at 5 meters per minute. At what rate is the distance from the balloon to SAM increasing when its horizontal distance from SAM is 20 meters? So let's start off by identifying what we know for sure. So we know this distance is 60 meters, and that's never going to change. So the balloon will maintain its altitude even though it's moving at 5 meters per minute. So it's always going to be 60 meters above SAM. So if we move the balloon to whatever position, we can come up with some variables. So this is going to be a right angle. We know that's 60 meters. Let's call this distance x, and the straight line distance from the balloon to SAM s. So what we need to find, at what rate is the distance from the balloon to SAM increasing when x is 20 meters? So what we need is ds dt when x is 20 meters. So first thing we need to do is come up with a relation between s and x. So what we can do, because s is the hypotenuse of this right angle triangle, we could say that s squared equals 60 squared plus x squared. So then if we want to find s, what we would do is just square root both sides. So we can do like this. So if we were to do ds dt of this equation, 1/2, and then it would be 60 squared plus x squared under the root symbol, and that would be multiplied. We have to do chain rule to that. So we would have to do 2x. So the derivative of 60 squared is 0. The derivative of x would be 2x. And then we multiply that by dx dt. So there's a few things we know with this. We're interested in ds dt when x is 20. So what we can do with this is sub 20 in there. We can sub 20 in here. And we know dx dt is 5 meters per minute. So let's make those substitutions, and it looks like we'll be able to figure out what ds dt is. So what we can do is eliminate those. 20 up top, 60 squared is 3600. 20 squared is 400. Square root that, and then multiply by dx dt, which is 5. Under the denominator, simplifies to give 4,000. Still under 20, and then multiplying by 5. We can multiply the numerators and get too much. Multiply the numerators and get 100. Still over 4,000. We can factor out a 400 from inside here. The square root of 400 is 20. And this would eventually simplify to give 100 over 20 root 10. And then this we can simplify further to 10 over 2 root 10. And then 10 divided by root 10 is the same as root 10. So it'd be root 10 over 2 meters per minute. And that's our final answer. Moving on to question 10. If x cubed minus 3xy equals 12 and dx dt equals 6, then determine dy dt when x equals 3. We need to figure out dy dt. We can apply chain rule to figure out what dy dt is. Now we have an equation with x and y, so we can go dy dt. What we can do is determine dy dx and multiply it by dx dt, which we know, and when we do this, it'll give us dy dt. It has to be done when x equals 3. So let's start by figuring out dy dx using this equation. So we'll need to do implicit differentiation to this and see if we can get a dy dx out of it. We'd have 3x squared minus 3, and we're going to have to do product rule to this. So derivative of the first times the second, which would just be y. So derivative of the first, x, with respect to x is 1. So I would have a 1 there, which I'm just going to not write. And then the derivative of the second times the first. So it would be x dy dx equals 12. So the derivative of 12 with respect to x is just 0. So we'll be able to get a dy dx out of this equation as long as we know what x is, which we do. So we can sub a 3 in there. But we also need to know what y is. So because we have an equation relating x and y, what we can do is just sub in 3 for x and then solve for y. 3 cubed minus 3 times 3y equals 12. 27 minus 9y equals 12. Simplify, we can subtract both sides by 27. So we'd have negative 15, and then divide both sides by negative 9. So we would get 5/3. So now we know what y is. We can sub that in here. So let's make our substitutions and figure out what dy dx will be. So this will be 27. This negative 3 needs to distribute into each of those things. So negative 3 times 5/3 will just be negative 5. And then negative 3 times positive 3 will be negative 9. Negative 9 dy dx. And now we just need to isolate for dy dx, which you can see would eventually be 22 over 9. So we have one major piece to put in there, and we know dx dt as well, which is 6. So dy dt then will be 22 over 9 times 6, which we end up with 44 over 3. And that's our final answer. Now for the last question of the day. At 1 p.m., boat A is 25 kilometers north of boat B. If boat A is sailing west at a rate of 16 kilometers per hour and boat B is sailing south at 20 kilometers per hour, determine the rate at which the distance between the two ships is changing at 1:30 p.m. So I've already drawn a diagram, which is generally helpful in this type of question, and we need to identify other stuff we know and figure out what we need to find. So the first thing we have, 25 kilometers due north. So we know this distance here is 25 kilometers. Something else we know, boat A is sailing due west at 16 kilometers per hour. Another bit of information we have is boat B is sailing south at 20 kilometers per hour. And we need to determine the rate at which the distance between the two ships is changing at 1:30 p.m. So 1:30 p.m. is 30 minutes after the start time. So what we can say is 1:30 p.m. is 0.5 hours. And we should have it in hours because our speeds are in hours as well. So that means that we're basically saying that 1 p.m. is time equals 0. So if we advance this system a little bit in time, A would end up over here and B would end up down here from their original positions. It would be helpful to draw some reference lines in here. So boat B is now 25 kilometers plus a little bit extra, however much it travels in half an hour. And boat A is now however far west it travels in half an hour. And we need to determine the rate at which the distance between the two ships is changing. So the straight line distance between the two ships is given by this line here. And I'm going to call this distance S. I'm going to call the distance that A travels from its initial position A, and I'm going to call the distance that B travels from its initial position. So S is related to A and B. They are on a right angle triangle. S squared is going to be given by A squared plus this length, which is 25 plus B squared. We need to figure out what ds dt is when time is 0.5 hours. We'll also need to know what A and B are at 0.5 hours. So B, because it travels 20 kilometers per hour, we can use v equals d over t. So velocity is distance over time. The distance is given by velocity times time. So we can go velocity times time. So if we multiply 20 kilometers per hour times 0.5 hours, that's 10 kilometers. So at 1:30, B is 35 kilometers south of A. And A, traveling at 16 kilometers per hour, we can get its distance by multiplying velocity times time. So we would do 16 times 0.5 again, and that would be 8 kilometers. So at 1:30, A is 8 kilometers west of its initial position. So in order for us to figure out what ds dt is, we can take this equation and do some implicit differentiation to it and see if we can get ds dt isolated. So this will be 2 s ds dt equals 2a dA dt plus 2 times 25 plus b times dB dt. We know already that dA dt is 16 kilometers per hour and dB dt is 20 kilometers per hour. We need to find out what ds dt is, but there's a few other things that we need to figure out before we can find ds dt. So we'll need to know what s is, we'll need to know what a is, and we'll need to know what b is. So we've already figured out what a and b are. So a is 8 and b is 10. So I've called this b. So at 1:30, b is 10 kilometers south of its starting point. And now we just need to figure out what s is. So if we're going to figure out what s is, we're going to use this equation. I know what a is at 1:30, that's 8. And I know what b is at 1:30, that's 10. So what we would do is square root both sides of this equation, sub in what you know for a and b. So a is 8 squared, and then you're going to add 25 plus 10 squared. And after some simplification, you'll get square root of 1289, which is about 35.9 kilometers. So that's this distance here at 1:30. So now we have, I think, everything that we need. That was 35.9 kilometers, or root 1289. So we can now isolate for ds dt. That would be 1 over 2s times 2a dA dt plus 2 times 25 plus b dB dt. So we can divide out the 2's. So if this half was distributed into each term, the 2's would disappear. And now our expression for ds dt is a little bit simpler. So we can sub in for s, which was root 1289. We can sub in for a, which is 8. We can substitute for dA dt, which is 16. 25 plus b, we know b is 10, so that'll be 35. And then dB dt is 20. So after some simplification, we will have then 828 divided by root 1289, which is about 23.06 kilometers per hour. And that's our final answer. So your question for today is in the textbook. It's on page 145. This is the one and only one I'd like for you to do for sure. You're welcome to try some of the other ones in the set for today, but this one should be submitted by the end of the day. And that's it. See you next time.